Let's wait for a couple of minutes, then I will start. Okay, let me start. So this is the 10th week of the problem solving session, Introduction to Atmospheric and Space Science. Today mostly we will discuss about the assignment questions. First, about the week 10 assignment questions and some numericals based on week 10. And then I will start with the particle description of plasma, then uniform and static electric field, and I will talk about the uniform and static magnetic field, what happens to the plasma if we treat it as a particle, and certain derivations, and then frequency and radius of gyration, and the case of electric and magnetic field In brief, I will give some description, and after that some numericals which will be helpful for people to do the assignments of week 11, and that's all. Therefore, let's start with the assignment questions. Okay. The first question of assignment 10 is, according to the Chapman's theory for peak production, at any height, the product of the number of molecules and the cross-section area should be. So the relationship is quite clear, that is Nm times sigma should be equal to 1, where Nm is the number of molecules and the cross-section area which one particular molecule faces is sigma, so the total will be Nm sigma is equal to 1. So this is a fact which we take in deriving this Chapman's theory of peak production. So I will write it just. So the first question is simple. Nm into sigma should be equal to 1, from which we get an expression that Nm is equal to sigma inverse. The sigma is area of cross section, and and Nm is the number of molecules. So this is the relationship. The second question is, the height of the peak production in the ionosphere is independent of. So let us write the expression of the peak production height of ionosphere, which we have derived earlier. So that is Hm, that is the peak production height, is capital H log of A rho H secant chi, where A is again the cross section. So it depends on the cross section area, it depends on the density, and it depends on the zenith angle. And of course this is the scale height. Therefore, if we go to the question again, then what are the options? One is scale height. So we have seen that scale height is there. Second is the incident radiation, which is not there. Third is the solar zenith angle, which is there. And fourth is the cross-sectional area, which is also there. Therefore, only the incident radiation is not there. Therefore, it is independent of the incident radiation. Third question is, according to the Chapman's theory of height of peak production decreases as the solar zenith angle. In the previous session, I have drawn a graph which is something related to this. You can see that the peak production height, this is chi is equal to 0, this is chi is equal to say some 30 degree, and so on. Therefore, you can see that this Hm, let me draw it in so as chi decreases, you can see that the Hm also decreases, and the vice versa is also true. As chi increases in this direction as chi increases, the height of the peak production also goes up. Therefore, the correct option for the third question is, as the height of the peak production decreases, as the solar zenith angle also decreases. So decreases should be the correct option. This is the numerical question, the fourth question. Although there is some discrepancy here because both the options are correct, but still we have considered that the C option will be correct, A option is not correct. There is some problem from the NPTEL part. Okay. Fifth question is, I will do this particular problem, the fourth one. Fifth problem is, which of the following is or are not the criteria for the plasma? First is given as Nd is much greater than 1, and we know that particle in the device sphere, this is the fifth question, so we know particles in device sphere, in fact we have calculated also some questions we have done, is much greater than 1. It's true. So this is perfectly fine. Okay, another expression, the second thing is that omega t is less than 1. Sorry, omega t is greater than 1, I think. Yes, omega t is greater than 1. So if you see omega t is greater than 1, I have given in the previous class one formulation about the relation between omega and t, that is, I have given that omega t is actually 10 by 9. So omega t is greater than 1 is also a correct option. But if you see this one, the third option, lambda d is less than omega t. Just check the units. Lambda d is in meters. It is a unit of length. But you see omega t, omega is the frequency of the plasma, and we know that what is the unit of frequency. So if you see, this is the thing which they have given, omega t, just a minute, yeah, omega t is greater than lambda d. So this is particularly length. But if you see this omega t, this is 1 by second into second. So this is some unit kind of, but this is in length. Therefore, this option is the only option which is not true. So this is not true. Sixth question is, the device shielding will be perfect in the plasma if there will be, see, if there is a very high temperature, then thermal motions will exist, and this thermal motion will not allow the electron clouds to form properly, because we know that thermal motions leads to this electron cloud formation in the plasma. So if you see the sixth question, this is the plasma, and you have a positive test charge, so the electrons are well surrounded as a cloud. Okay, but if there are thermal motions, if thermal motions are present, then this cloud will not form properly. Therefore, this electron cloud formation requires no thermal motion. Fine. no thermal motions is a perfect thing for Debye shielding process in plasma. And all others are the numerical questions except for the last one. So the last one I will take, and other numerical questions I have already given. So we will solve all those questions. But the 10th question is the value of the electric potential phi r for the Debye sphere is given by, see this phi naught, you have to understand by your own way that this phi naught is the Coulomb's potential, that is kq by r, and then you have e to the power minus r by lambda d as the correct Debye potential formula. So let me write it, and this will end the assignment discussions. Although some numericals are left, that numericals we will take up one by one. So the Debye potential, just a minute. So this phi of r is given as 1 by 4 pi epsilon naught, which is that k into q by r if the test charge is positive q, and e to the power minus r by lambda d. So it is not only that the Coulombic potential which is existing, but there is some extra term which is also there, and therefore that is actually been written as, this is phi naught e to the power minus r by lambda d. This should be the correct option. And if you see here, B option is correct. Phi of r is phi naught e to the power minus r by lambda d. So all the other numerical questions we will solve now one by one. This 9th question, 8th, 7th, and this question, question number 4, where two options are given with same unit, absolutely same values, but one is considered to be correct, one is not considered to be correct. So that is the problem of the question, but we will solve. We have to understand those things, concepts. Okay. Yeah. The scale height for hydrogen atom at a temperature of 300 Kelvin will be. So see, given that this is a hydrogen atom, so what will be the molar mass for the hydrogen atom? It will be 1 gram per mole. Right? I need to find out the scale height. And what is the formula of scale height? We have done too many times. What is the scale height? It is nothing but R T by G. Simple. And the scale height calculation for a particular temperature, that is an isothermal atmosphere we generally consider. So here also we will consider an isothermal atmosphere kind of, and this temperature is given to be 300 Kelvin. We don't need to change it into Celsius or something else because it is given already in the SI unit Kelvin, right? G is known. Only thing which we need to calculate is R. What is this R here? Again, to revise the fact, this R is the specific gas constant. Okay, this R is the specific gas constant, and how to calculate that is nothing but R star by A. Therefore, R star is known to me, it's 8.314 joules per Kelvin per mole, and divided by this mass is 1 grams per mole. We need to convert it to kg, so you have to multiply by 1000. So what I get is 8314 joules per Kelvin per kg as R for the hydrogen atom. Put that to calculate the scale height, so that will be RH into T, that is 300 Kelvin, divided by 9.81, and this RH comes out to be 8314 into 300 divided by 9.81. So let's calculate it. Just a minute. Let me calculate and put the answer. So 8314 into 300 divided by 9.81. So it comes out to be about 254.25 kilometers. The answer given is 254.51. So that answer is correct. So this is the answer. Right? So two options are given there with same unit and same thing. So ideally I think the solution should be in meters. One of the options should be in meters, another will be in kilometers. And but unfortunately the might be due to the printing mistake, the two options are same. But this should be the correct option. Okay. The next numerical is based on the d by length. D by length, if the charge density is given and kT is given, already helped us in calculating. I will write the d by length formula first. So this is the d by length. So d by length, lambda d is equal epsilon naught kT divided by n naught e square. Right? Now epsilon naught is known, so that is 8.85 into 10 to the power minus 12. KT is given to be as 0.1 electron volt. Okay. Now what is this 0.1 electron volt? So this 0.1 electron volt is nothing but 1.6 into 10 to the power minus 19 joules. Right? So this is now done. Another is n naught, which is given charge density 10 to the power 12 per meter cube. And E square, E is also the charge of the electron, that is 1.6 into 10 to the power minus 90. Fine. So now we can easily calculate the lambda d just putting the expressions. So therefore we are getting 8.85 into 10 to the power minus 12 into 0.1 into 1.6 into 10 to the power minus 90 divided by, this is 10 to the power 12 into 1.6 into 10 to the power minus 19 whole square. Okay. So now just separating the powers and writing it. So it is 8.85 into 1.6 divided by 1.6 whole square. Just writing the other things, and this is C, this is 10 to the power minus 1, so makes it 10 to the power minus 20 with this 10 to the power minus 20 and 12, so it's 10 to the power minus 32, and 10 to the power minus 19 square is 10 to the power minus 38. So 38 will come over here, so it will be 10 to the power 6. Right? Let me write it properly, it will be helpful to understand. So this is 10 to the power minus 12 into 10 to the power minus 20 divided by 10 to the power minus 38. So if you do it, so 1.6 chops out, so it becomes 8.85 divided by 1.6 into root over 10 to the power 6. So it comes out to be about 2.35 into 10 to the power there is a 10 to the power 12 which is also present here, that makes it 10 to the power minus 3. This will be 10 to the power minus 6. Okay, so that will be in meters. Right? So this will be the correct option. And if you see the assignment question here, This we have checked, it is 254.51 kilometers, and this is comes out to be 2.35 into 10 to the power minus 3 meters. This is the 7th question. So this is solved now. We will solve the 8th and the 9th question now. Yeah. Just a minute. In a laser fusion, the core of a small pellet is compressed to a density of 10 to the power 26 per meter cube at a temperature of some 50 million Kelvin. The number of particles in a device sphere in this plasma will be. So number of particles in device sphere is given by, let me give the expression first. Number of particles in device sphere is given by the Debye parameter, that is lambda is 4 by 3 pi lambda d cube n naught. Okay, now n naught is given to me, lambda d has to be calculated, which we can do it based on the number density which is given and based on the temperature which is given. Nothing else is required, because if you see the expression of lambda d, which we have written earlier also, that is epsilon naught, which is a constant, k is a constant, t is the only unknown, n naught is also an unknown, and e square is known. Therefore, if you just put the expression, so what it will be, 8.85 into 10 to the power minus 12 into 1.38 into 10 to the power minus 23 times 50 million Kelvin divided by n naught is 10 to the power 26 into 1.6 into 10 to the power minus 19 whole square. This is the your Debye length. Therefore, this lambda d, what it will come out to be, so if we solve it further, so it comes out to be, I just separate out some particular things like 8.85 into 1.38 into 5 I have done, divided by 1.6 into 1.6. Okay, all powers I have separated here. So what are the all powers? So powers are 10 to the power minus 12, 10 to the power minus 23, and 10 to the power 6 into 10, that is 10 to the power 7, divided by 10 to the power 26 into 10 to the power minus 38. Fine. So it comes out to be, see, 10 to the power minus 23 and 12 becomes 35, and minus 26 will also come. So all this power, if you do it separately, then it comes out to be, just write it properly. See, 26 minus 38 is 10 to the power minus 12. So this 10 to the power minus 12 and 10 to the power minus 12 can be chopped out, and so 10 to the power minus 12 divided by 10 to the power minus 12 into 10 to the power 7 minus 23. So this goes out. This is 8.85 into 1.38 into 5 divided by 1.6 into 1.6, and again if we write it properly, so it becomes lambda d. This is actually 4.88, and this comes out to be 10 to the power minus 16, so root, so 10 to the power minus 8 meters. Okay, but what we need is lambda d, this is capital lambda. So this capital lambda will be 4/3 into 3.1416 into 4.88 into 10 to the power minus 8 whole cube into 10 to the power 26, right? So this comes out to be 486.79 into 10 square and comes out to be 4.86 into 10 to the power 4. This is the number of particles in a device field. So just check it. Yeah, 4.86 into 10 to the power 4 is the correct option. And the last question which is left in the assignment is the plasma frequency based question, which we have already solved, just 9 root n naught. We will do it again and complete the assignment of the 10th week. And then we will start with some concepts of the 11th week and some particular concepts which are helpful for solving the week 11 assignments, and some numericals based on that, which will be also helpful to solve the numericals of assignment 11. So that also we will see. Okay, now this is the last question. So calculate the plasma frequency F for electron if the electron density is 4 into 10 to the power 10. Okay, so this plasma frequency is given as 9 root n naught. Given n naught is 4 into 10 to the power 10 per meter cube, right? Therefore omega is, or let us write it, F is 9 into root over 4 into 10 to the power 10. So it is 9 into 2 into 10 to the power 5. So it is 18 into 10 to the power 5. So it's 1.8 into 10 to the power 6, or it is 1.8 megahertz. So this is the answer, 1.8 megahertz. So if you see and confirm it, so it is 1.8 megahertz, which is the correct option. So we have seen all the questions of this assignment 10, and now we will go towards the week 11 problems, which will help us to solve the assignment questions for the 11th week. So now we will go to the descriptions of the assignment 11 or week 11 concepts. Okay, just a minute. Okay. So particle description of plasma is the next topic which we will take. But before that, just to recap what we have seen about basic things about the ionosphere, is that shortwave radiations results into formation of ions. So obviously some molecules and atoms are there in the atmosphere, and shortwave radiations like X-rays, UV, extreme UV, all these things creates these ions. And of course during the night time the ions production is less. But when we will consider it to be a particle description of plasma, because we know that plasma has a huge amount of ions and electrons, but when we will consider that plasma as some particles, we will consider plasma to be particle only when the concentration is very low. So when there are low electrons and ions, then we treat them as single particle. So when we are considering the particle description of plasma, whenever the concentration, so concentration of electrons or ions are present in very less number. Then only we consider it to be a particle description of plasma. So in this particle description, what we will just do, we will apply an electric field, we will apply some magnetic field in a particular direction and see what will be the influence of this on plasma particles. And these plasma particles are nothing but electrons and ions. This is what our plan is to see. Okay. Okay, but before that, let me add one of the slides. Just a minute. Yeah. Okay. So here we know that Lorentz force when both magnetic and electric fields are present, F becomes equal to Q times E plus V cross B, where B is the magnetic field, E is the electric field. So this is the electric field and this B is the magnetic field. Right? Now we already know that del dot B is 0. So divergence of the magnetic field is 0. Now if we can write this, then we can also write that B is equal to del cross A. This is the magnetic potential. Right? Also we know that del cross E, these are all Maxwell's equations, delta B, delta T. Therefore, del cross E can be written as minus del T of del cross A, because B is del cross A. Now I take it on this side, so it becomes E plus delta A delta T. This is magnetic vector potential. Remember, this is a vector potential that should be equal to 0. Therefore, E plus delta A delta T should be some minus gradient of phi. Why? Because curl of gradient of phi is 0. Therefore, E will be equal to minus grad phi minus delta A delta T. Okay, so this is the preliminary thing. Okay, so if we consider Again, we are talking about plasma as a particle. So if we consider plasma particle having mass m and charge q, then the total force on this particle will be q e plus v cross b, which we have written the Lorentz force, plus m into some r. So these are the non-electromagnetic, like gravity or all those things, non-EM forces, and this is the electromagnetic forces. Mostly we will discuss on this particular thing. Okay. Now we will go to the electric field case, where we will apply only the electric field. So this is not the steady, but this is static. Okay, so this is uniform and static electric field. First we will see the uniform and static electric field case, where a charge with a particular mass is placed and how it behaves, what is the equation for those, and we will derive what will be its expression of velocities, and we will see what is the energy of those particles, and then we will switch on to the uniform static magnetic field, because these are the very basic and fundamental things which we need to know in this particular week on this particular session. And as we go ahead, then we will just write briefly about what will happen when electric field and magnetic field both are there, and we will see certain expressions of the velocities in that case also, and some particular important expressions which I will just write. I will not derive too many things because it's too much of derivation, which will not be able to cover in this particular session. Okay, and then do some numericals that will help you to solve the assignment problems. Okay, since these are the basic and preliminary things, so I will derive these particular things. Okay, the first is the uniform and static electric field. So what is this uniform? Uniform means that delta E delta R is 0, and static means delta E delta T is also 0. Okay, but E is only present as Ez. Only in the Z direction, that is the electric field is present. So this is suppose your X, this is suppose your Y, and this is suppose your Z. So electric field E is equal to Ez is in the k cap direction. Okay, in the Z direction. Now if you have a plasma particle whose charge is Q, whose mass is m, and it is coming like this over this electric field which is directed in the Z direction, what will be the influence and what will be the change in the velocity of this particular particle, that we need to see. Now since we are not considering any magnetic field, just keep the magnetic field 0. Okay, therefore Lorentz force becomes what? Therefore Lorentz force becomes F is equal Q into E, right? Q into E is the thing which we will get, or m dv dt, the mass into acceleration, that is the force, Q into Ez, isn't it? This is what we get. Now we can write this into 3 components, the scalar components, right? So it will be m dvx dt will be equal to 0, m dvy dt will be equal to 0, and m dvz dt will be equal to qez, right? Therefore before that, just some initial condition if we use, then it will be helpful for understanding. So let us consider I will write this as the initial conditions. Okay, let Vx t is equal to 0 is Vx0, Vy at t is equal to 0 is Vy0, and Vz at t is equal to 0 is Vz0. Just write it like this. Okay, now this is the initial condition. Now what we are getting here is that m dvx dt is equal to 0. Therefore Vx is constant, and what it will be its value? Whatever was there at t is equal to 0, because it is not changing with time, so it is Vx0. Vy also is constant, so whatever the value it was there in time t is equal to 0, that is the same. So Vx and Vy are constant. So in the x and the y direction, the velocity remains constant. Whatever is the initial velocity, that is the same velocity which is remaining. But only thing, what will happen at Vz to the Vz? So let's check it. So m dvz dt, so let me write it. So dvz by dt is actually q by m ez, isn't it? Okay. So now if we integrate it from Vz0 to Vz, and this becomes q by m ez dt 0 to t, right? Just writing the expression. So what I will get is Vz minus Vz0 will be equal to q by m ez into t. So Vz becomes Vz0 plus q by m ez into t. You can see that with time Vz showing a linear relationship. Okay, linear relation with time. Okay. Now in this electric field thing, another thing can be done. So if you have some electrons and ions which are positively charged, electrons are negatively charged, and you have an electric field here, you give both the electrons and ions. So ions will move in this direction, but the electrons will move in the opposite direction. So charge separation can be a big thing or a big process which can be done using the electric field only. Okay, so this is a small concept of charge separation. Okay, another thing which I will show you is that about the energy. Okay, so if you write the momentum equation, so m dv dt q into e, full vector form is this, right? Now if we just dot it with velocity, so it becomes q e dot v. Now this thing can be written as d dt of half mv square, isn't it? You do it, it will come out to be the same, and that will be equal to q e dot v. Now E is equal to minus gradient of phi, right? Because no magnetic field is there, so if you just write del cross E is equal minus delta B delta T, but since no magnetic field is there, so del cross E equals 0. Therefore E can be written as minus gradient of phi. Therefore we can write d dt of half mv square will be equal to q of minus grad phi dot v. So if we write it properly, so So what I get, minus delta phi delta x I cap minus delta phi. Let me take minus outside. So this is plus delta phi delta y j cap plus delta phi delta z k cap dotted with delta x delta t I cap, the u, or vx, delta y delta t j cap, and delta z delta t k cap. So if we write it properly, so it becomes minus q d phi dt, because phi is now complete function of time. Right, so what I get is d dt of half mv square plus q phi is 0. Therefore, half mv square plus q phi is constant. So this q phi is the electrical energy and half mv square is the kinetic energy. Is actually the potential energy, I would say. In electrostatics, this is the potential energy. Okay. So what conclusion which we are drawing here from here? So we have already seen that this is the big conclusion, that linear relationship with time. So particles' velocity is linearly varying with time. And the second conclusion is this, that the total energy is conserved. Therefore, work done will be 0. So the net work done will be 0. This is the conclusion which we are deriving from this energy conservation equation. The immediate next thing where we will go is somewhat more, derivation is much more as compared to this. This is a very simple case which we have seen in the normal electric field, that too in one direction. But in case of uniform static magnetic field, the case will be somewhat more, derivation will be there, and we will see certain expressions of particular things like radius of gyration and cyclotron frequency and all those things. Okay, so just a minute. Now, as we have seen in the earlier case, that for uniform and static electric field, we have considered that the B is completely 0. So here also we will consider that E is 0. Electric field is 0, only magnetic field is there also, but since it is a static magnetic field, so delta B delta T should be equal to 0, and dB dZ is also equal to 0. Okay. So what does this mean? It means that B is only acting in the Z direction. So this is your X, this is your Y, this is your Z. So this is the BZ direction. Okay, and again a Q with charge, particle with charge Q and mass M is going towards this direction with a velocity V. So what is the influence of this only magnetic field which is there in the Z direction? What is its influence on this particular particle? This is what we need to see. But before that, we can easily derive about the energy. So what is the expression of the force? The expression of the force comes out to be F is equal to Q into V cross B. Right? Now, since V cross B is the direction where V is suppose here, B is here, and this is the force. then only that is a cross product, right? So if this is the cross product, or just right, the force will be in the opposite direction. Just a minute, this is V and this is suppose B, but what we can see is that this force is perpendicular to both V as well as force is perpendicular to B, but displacement will be in the direction of the velocity, but we are seeing that force is therefore perpendicular to the displacement. Okay, so force, if it is perpendicular to the displacement, what happens to the net work done? So the net work done again in this case is nothing but F dot S, and that will be having 90 degree in between, so it is 0, right? So net work done here is also 0. That concludes what? One first thing is that net work done is equal to 0, and the second thing is that energy is therefore conserved, which we have seen in the earlier case also, that energy is conserved means the net work done is 0. Similarly, the net work done is 0, means energy is conserved. So energy conservation is seen here also in a uniform static magnetic field. Energy conservation was there also in case of the uniform and static electric field, right? Okay. Now we will derive the expression of the Vx, Vy and Vz. Okay. So F, again, because there are no electric field, so we can write m dv dt is equal q into v cross b, right? So now V again can be written as Vx I cap plus Vy j cap plus Vz k cap. Now we define two things. One is the perpendicular velocity and is the parallel velocity. So these are the perpendicular velocity. We call it V perpendicular, but this is V parallel. Why? Why Vz is V parallel? Because this is parallel to magnetic field, but this is perpendicular, right? This is just to show the expression. Now V cross B, so you have to do your cross product, so let's do it. So it's V cross B. Let us do this thing. So this is I j k, so this is Vx, Vy, Vz, Bx, By, Bz, right? So I get, so this Bx is 0, By is 0, only Bz remains. Therefore I can write I cap Vy Bz, it's 0, minus j cap Vx Bz minus 0 plus k cap completely 0. Therefore what we are getting is m dvx dt is q vy bz. Similarly, m dvy dt is equal minus q vx bz, and m dvz dt is equal 0. Okay. So if you remember that in the electric field case, we are seeing that in the z direction only the electric field is there. Now we have kept magnetic field also in the z direction. But see the expression change. Earlier case, m dvx dt was 0. In the y direction also the momentum equation was 0. But only in the z direction, Vz was linearly related with time. But see in this case, in the magnetic field case, you have x and y, but you don't have anything in z, right? So this is the difference between the electric field and the magnetic field, although uniform and static. Okay, let's solve these expressions and see what we get. So just solve this particular expression first, the easiest one, that is this one. So let us consider first again the initial conditions. Initial conditions is that Vx again at t is equal to 0, it's Vx 0, Vy at t is equal to 0 is Vy 0, and Vz at t is equal to 0 is Vz 0. Therefore, from this expression it is clear that Vz is constant, and therefore we can write Vz is equal to Vz 0. Simple. This is the number one thing which we are getting. Right? Okay. Now we will solve these two. How to do that? Let's see. Okay, so let's write m dvx dt, which was having the expression of q vy bz. Right? Okay. Now I write, oh sorry, so I write dvx dt is q by m vy bz. Right? Now what I do is that I double differentiate it. So d2vx dt2 will be equal to q by m vy. So it becomes dvy dt into bz. What I get is q by m. Now what is dvy dt? Is actually minus q by m vx bz into bz. So we are getting minus q square by m square bz square into vx. So ultimately we are getting d2 vx by dt2 plus q square by m square bz square vx should be equal to 0, which is a very well known differential equation, and we call this particular thing as omega square. This is actually the cyclotron frequency, right? So therefore omega square, let me write, it is q square bz square by m square. Therefore omega will be equal to q bz by m. Simple. And now what will be the expression of the velocities? It's very simple. In the same way also you can calculate. So let me write it. In same way we can see and derive Vy. So ultimately what we can see from this expression is that it represents some kind of an oscillatory motion. Right? It represents some kind of an oscillatory motion. Therefore Vx can be written as a cos omega t, the general solution for this sine omega t. Right? And let me write dvx dt minus omega A sine omega t plus b omega cos omega t. That's all. And let's write, let me see whether this is valid or not. Well, it will be valid, minus a omega square, and you have minus b omega square. So what I get is minus omega square again Vx, right? So this is satisfied. Now we already have seen the initial condition that at t is equal to 0, Vx is equal to Vx0. Therefore at t is equal to 0, you have only a, because b, the second expression, if you see, at t is equal to 0, sine of 0 is 0. So a is equal to Vx0, right? Therefore we can write the Vx based on this particular initial condition as Vx0 cos omega t plus b sine omega t. Correct? Now dvx dt, the expression of dvx dt is known to us. So it is minus a omega sine omega t plus b omega cos omega t. And dvx dt we know is actually q vy b by a, right? Therefore what we are getting here is, so omega qb by m is omega, right? So omega vy, let us take out the omega here, minus a sine omega t plus b cos omega t. Chop out this thing, and we know that at t is equal to 0, again Vy0 will be what? B. Because at t is equal to 0, only this cos will be 1, but sine will be 0. Therefore we have got B, we have got A, right? Just write that in this particular expression. So Vx will be equal to Vx0 cos omega t plus Vy0 sine omega t, right? And as you can see, the expression of Vy, this is the Vy, is minus a sine omega t plus b cos omega t. So from here we can directly write Vy will be equal to, see, minus a, so it will be minus Vx0 sine omega t plus Vy0 cos omega t. So these are the expressions for the Vx and Vy, which is denoting some kind of an oscillatory motion. Okay, and already we have found out that Vz is equal to Vz0. This is constant, okay, in the z direction. Now if I now somewhere do this thing, that is Vx square plus Vy square. So let's do it. So this will be Vx0 whole square cos square omega t plus Vy0 square sine square omega t plus 2Vx0 Vy0 sine omega t cos omega t plus Vx0 square sine square omega t plus Vy0 square cos square omega t minus 2Vx0 Vy0 sine omega t cos omega t. So these can be chopped out, but and this, if you see, it comes out to be nothing but Vx0 square plus Vy0 square. So what does this represent? This is some kind of a circular motion. in the velocity plane. So this is what it is, some kind of a circular motion in the Vx, and this is Vy. Right. Now if you see the position also, there also you can see how we can get, say, dx dt as Vx0, which we see. This is cos omega t plus Vy0 sin omega t. Therefore x will comes out to be Vx0 sin omega t by omega, just integrating it with respect to time, and Vy0 by omega, and sine integration becomes minus cos, isn't it? So this is what we are getting. Similarly, we can write the expression of y. Again, I have to just include a slide. Just a minute. Yeah. Okay. So now we are again getting this y will be equal to again Vx0 cos omega t by omega, Vy0 sin omega t by omega. That is what we are getting. And again use square and add. So the position vectors also gives you some kind of a circular motion. Now this Vx0 square plus Vy square, we can somehow write it as V perpendicular square by omega square. This is kind of a radius squared. This is what the expression of the circle, right? This is the position. So what is happening actually? The thing which is happening is that there is a circular motion and it is moving in the z direction because Vz is constant. So there is a continuous Vz and the Vx Vy is having a circle. So ultimately resulting into a helical motion. So Vx and Vy, which is in the perpendicular to the magnetic field, these are represented by the circles, okay, with time. But the Vz is constant, as a result of which a helical motion can be seen. Okay, so this is the radius. So Vx, Vy, which are nothing but the V perpendiculars. This is represented by a circle. Okay, but this circle is moving in the z direction. In the z direction with constant speed Vz0, and that's why we are getting something like this, okay, helical motion. And we write the radius as V perpendicular by omega, and we know that the expression of the omega, what is that? QB by m. So it is V perpendicular m by QB. Right? Now I go to the next slide. Frequency and the radius of gyration. This is nothing but what we have derived so far. We will write one by one. See, the radius, we have got an expression. We have got an expression of the frequency or the angular frequency, whatever you say. So what we will see is that here we will see what is the cyclotron frequency, maybe the angular frequency, what is the cyclotron frequency, the actual frequency, time period, and radius of gyration, which we call as the radius of gyration. Okay, and we will just define one statement of guiding center, and that's all here. After that we will take some cases of electric and magnetic field, both are there, and we will not derive it, just put some expression which are important about the drift velocity and all those things. Yeah, this is the thing. And then we will start the numerical based questions. So I have put here 5 questions. Okay. So what we have seen is that the omega, what we call as omega c, so cyclotron angular frequency, we have seen this, and this is only coming in the magnetic field. So omega c becomes q b by m, right? This is the expression. Then what will be the cyclotron frequency? Just divided by 2 pi. So cyclotron frequency becomes fc, that is omega c by 2 pi. So it will be nothing but qb by 2 pi m. And what will be the time period? Just 1 by that thing. It will be just 2 pi m upon qb. The radius of gyration, which we have just now derived, that is nothing but the radius of that circle, which this particular radius. Suppose this is the center and this is the radius. So this is the expression of this radius of gyration. So this radius of gyration is m v perpendicular divided by qb. V perpendicular, it is in the direction of the magnetic field, because we have considered the direction of the magnetic field to be in the z direction. Okay. Now just check it from this particular radius of gyration formula. What will happen in case of ions? See, ions have greater mass than electron. Therefore, ions will have larger circles than electrons. In fact, if you can see the protons and the electrons, so proton circles are much higher as compared to that of the electrons, which we will see in just the numericals which I have given. Okay. Now another thing which is important. So another thing is that this, because the charge is also having some positive and negative thing. So suppose this is the z and these are x and y. So in case of ions, same thing happen but with larger radius. If it starts in this direction, you find that in case of electrons, they will start in the opposite direction and will have smaller circles. Why smaller circles? Because the radius will be small, because it is proportional to m. So this is the case of electron. It will move in this direction, in just opposite to that of the ions. This is another thing which I have to say. Another is the guiding center. What is this guiding center and its definition? Imaginary point surrounding which circular motion takes place. So you can see that this axis, if you consider, that is nothing but the guiding center which is moving. Okay, so this is the thing about the guiding center, and we have completed the uniform and static magnetic field case, which we have derived so far, and uniform and static electric field case, considering the particle nature of the plasma, which we can only treat when the concentration of the plasma particles are extremely small. Then only we can consider that. Now is the condition for the electric and the magnetic field, both are present. In brief, I will just tell what will be the expressions of Vx, Vy and Vz. What will be the drift velocity in this case. So I will not derive too many things. Okay. So here, so you have both the Q or the charge which is present of the plasma. It can be both positive as well as negative, which we have considered in the previous cases also. You just put the charge in Q expression and you will get the result. Okay. So here one of the fundamental thing which we have used, that is electric field is perpendicular to B, and it is something like this. So this is the Z, this is X, this is Y, and suppose the electric field is in this direction and the magnetic field is at BZ. Okay. So now therefore electric field is in Ex, 0 Ez. The entire derivation is there in the lecture, so you can always see that. So I am not deriving it, just some particular results I am writing. But in this case, what we have to write is that this m dv dt, the entire thing we have to write, the q into E plus V cross B. In the earlier cases, when we are taking each and everything simultaneously, not simultaneously, separately, in case of electric field, we are not considering the V cross B part. In case of magnetic field, we are not considering the E part. But here we have to consider both. And in that case, what we will get is your Vz will come out to be Q by M Ez into T plus Vz0. So what you can see here is that again the linear relationship with time which we have seen in case of the electric field, uniform and static electric field, the same thing is happening here. Okay, this same thing is happening here as we have seen. But in case of Vx and Vy, there are some changes. So Vx becomes V perpendicular. This V perpendicular, remember, is Vx naught square plus Vy naught square, that thing, e to the power iota omega c t. And Vy, again V perpendicular, one iota is there and some plus minus charge. Plus minus iota V perpendicular e to the power iota omega c minus Ex by B. Now this extra part is nothing but the, we call as a velocity, because of course, because this is the Vy's expression, so this is nothing but the drift velocity. Okay, and there is another good expression for the drift velocity, same thing but using some complementary solution. And but before that, I want to say what is this omega c. This is same the cyclotron frequency which is given by QB by M. Same thing. And this is the angular frequency, remember this. So what we can see from here, Vz is linearly related to the time, so it's varying with time linearly. Vx and Vy are not linear in time. Again, the circular motion is preserved because of this iota thing, which is nothing but representing the oscillatory circular motion. So let me just write something like Vx, Vy are not linear in time. Second thing is circular motion is preserved. Okay, and again if we write this expression that m dv by dt is nothing but q into e plus v cross b. We cannot neglect any term here, and they are just writing that v is equal to v1 plus v2, but this is the particular solution which we have got, and this is the complementary solution. Differential equations generally has these two things. Okay, so this complementary solution can be found out using this. Let's put that equal to 0, and that is nothing but so q into e plus v2 cross b is equal to 0. Therefore, E will be equal to minus V2 cross B. And if I just write E cross B, just a minute. Again, have to take one extra slide. Just a minute. E cross B can be therefore written as minus V2 cross B cross B. And this is a vector identity. We can easily write V2B square minus B V2 dot B. And since V2 is not in the direction of the B, so this can be taken as 0. Therefore, we can write this V2 is E cross B by B square. This is the expression of the drift velocity. Drift of guiding center, the guiding center which we have just defined. But in this case, drift of the guiding center, that is the drift velocity. And another small thing which I should discuss, which will help in solving some assignment problems. So non-homogeneous fields, this non-homogeneous field topic I think is there in the week 12. So we will discuss in the next class in details. But in the non-homogeneous fields, there is a term called length scale or length scale of inhomogeneity. What is this? So up to this length scale, B is homogeneous. After that it becomes inhomogeneous. Means it will start varying with space. And after this, it becomes inhomogeneous. Right? And this RL or the radius of gyration should be always less than L. Then only this cyclotron or radius of gyration can be defined. So this is the radius of gyration, because we have seen that in case of the uniform magnetic field only, this RL can be defined. Therefore, this is the radius of gyration. So for inhomogeneous field whose length scale is L, so RL should be less than, very less than L. So this is what is your important condition. Okay, I will not discuss this inhomogeneous field or non-homogeneous fields in much more details. I will do it in the next class. Now let us see 5 numericals which I have put here, which will be helpful for solving some numericals in the next assignments. Okay. So this question is calculate the radius of gyration of proton with kinetic energy 15 mega electron volt and magnetic field of 0.35 Gauss. Okay. So first of all, let us write what are the things which are given. One is the mass of the proton is given, that is 1.67 into 10 to the power minus 27. But most of the cases it may not be given because it is known to people. Okay. B, magnetic field 0.35 Gauss. And what is the conversion to Tesla? It's 0.35 into 10 to the power minus 4 Tesla. Kinetic energy is given. What is this kinetic energy? Is half mv square or K. So that is 15 mega electron volts. So it's 10 to the power 6 into 1.6 into 10 to the power minus 19 joules. So it becomes 15 into 1.6 into 10 to the power minus 13 joules. This is also given. Now what we need to find is the radius of gyration R. What is the expression? mv divided by qb. I know what is the charge of proton. So what is the q? Is 1.6 into 10 to the power minus 19 coulombs. Right? So I know q, I know m, I know b. Now what about v? V can be found out from this kinetic energy. So let's find out v. How to find out v? So it will be 2k by m root, isn't it? So now if I just put this expression over this r, so we get r is equal to m root 2k by m divided by q into b. So this root m and this will cancel out, so becomes root 2 km divided by qb. Yes, so r is therefore root over 2 into given thing, that is 15 into 1.6 into 10 to the power minus 13 into the mass, divided by right q into b. B is 0.35 into 10 to the power minus 4. Correct? Now if you solve it, it comes out to be, let's see, let's see the powers. 10 to the power minus 27 and minus 13, 10 to the power minus 40. So it comes out to be 10 to the power minus 20 because there is a root, and this is 10 to the power minus 23. Right? And all other things let us calculate and see how much comes. So it's 2 into 1. 15 into 1.6 into 1.67. Yes, take the root of this. So it comes out to be 8.953 divided by 1.6 into 10 into 0.35. So let's do it. So it comes out to be 15.98 into 10 cube meters. This is the answer. Okay. It's a very large radius of gyration. So you can see that because the energy is so high that its velocity becomes so high, and we know that radius is proportional to the velocity. Okay, so this is a way of solving the radius of gyration questions. Okay, where kinetic energy is given and you have to calculate the radius of gyration. Okay. The second question is just a minute. Yeah, the second question is, if the radius of the gyration is 200 meters, what is the kinetic energy of the electron when moving in a magnetic field of 0.5 into 10 to the power minus 4 Tesla? Well, so what is given again? Just write this. So given radius of gyration, that is 200 meters. Okay, magnetic field is 0.5 into 10 to the power minus 4 Tesla. Kinetic energy I need to find out. And we have just now seen that K is equal half mv square, right? And we can write 2K by m root is actually V. And the expression of the radius of gyration is mv by qb. So if I put the velocity, it comes out to be root 2k m divided by qb. Now given that it is an electron, so the mass is also known, that is 9.11 into 10 to the power minus 31 kgs. So everything is known. R is known, m is known, q is known, and b is known. So what is q? Q is same, 1.6 into 10 to the power minus 19 coulombs. Just put the expression and get the k. How will I get? So qb into r whole square divided by 2m should be the kinetic energy, right? So just put the expressions. So 1.6 into 10 to the power minus 19 into 0.5 into 10 to the power minus 4, r is 200. Put that whole square divided by 2 times 9.11 into 10 to the power minus 31. This becomes my kinetic energy. So let's see how much kinetic energy it have. Okay. So just checking the powers. 10 to the power minus 19 minus 4, 10 to the power minus 23 square, 10 to the power minus 46 plus 31. Okay, and this is 1.6, 0.5 and 200. Let's do that. 1.6 into 0.5 into 200 square. So it comes out to be 25600 divided by 2.2 into 9.1. Let's divide by 2. So it comes out to be 1405.04 into 10 to the power minus 15, isn't it? Yes. So that is in joules, right? Now if you have to convert it into the electron volt, so just do it. 14.05 into 10 to the power minus 13 we can write in joules. So this will be nothing but in mega electron volt if you have to calculate. So 14.05 divided by 1.6. So it becomes 8.78 mega electron volt. So just you check it, 8.78 into 1.6 into 10 to the power minus 13, the same expression you will get. 1.405 into 10 to the power minus 12. That is same. So this is the answer, right? So this is the second question which we have seen. Third is, what will be the ratio of the radius of gyration of proton to electron if the velocities and the magnetic fields are same for a proton and an electron? So you have the same magnetic field. So just write the expression of the radius of gyration. Right? This is the expression. Now R for proton will be equal to MP by QP by VP by BP, and for electrons it is ME by QE VE by BE. Now given that VE is equal VP, BE is equal BP, and we know that QP is equal QE. We know this. Therefore, what is RP by RE is nothing but MP by ME, isn't it? And we know that this is 1.67 into 10 to the power minus 27 kgs. This is 9.11 into 10 to the power minus 31 kgs. So ultimately, this is the ratio of the masses which is playing a role here. So it's 0.1833 into 10 to the power 4, or it can be written as 1.83 10 cube. So it's a kind of 1,000 times, isn't it? Okay. Now 2 more questions are left based on some alpha particles and a question on the angular frequency, cyclotron frequency. Okay. So consider an alpha particle in a uniform magnetic field of this 0.05 Tesla having cyclotron angular frequency of this. What is its mass? Simple question. So given is this omega c cyclotron frequency is 2.39 into 10 to the power 6 radians per second, right? And the magnetic field is also given, that is 0.05 Tesla. Nothing to convert because it is already in the SI unit. If had it been in Gauss, so had it been in Gauss, we can convert it. Okay. Now given means I have to calculate the mass of the alpha particle. But we have to remember one thing, that the charge of alpha particle is 2 times the charge of electron. Therefore, the total charge will be 2 into 1.6 into 10 to the power minus 19 coulombs. This we need to know. Okay. Now, what is the expression of the omega c? Okay. So the expression of the omega c is actually QB by M. Therefore, the charge we have already seen that it is 2 times QE. Therefore, just put the expressions and find out the M. So M will be QB by omega c. So what is Q? 2 into 1.6 into 10 to the power minus 19 into B, that is 0.05, and divided by the omega c, which is 2.39 into 10 to the power 6. So if you just calculate it, let's see how much it comes. So it's 2 into 1.6 into 0.05 divided by 2.39. So it comes out to be 0.0669 into, now this is 10 to the minus 19 and 10 to the power 6 is also there, so it becomes 10 to the power minus 25 kgs. So it can be written as 6.69 into 10 to the power minus 27 kgs. Right? Now, just check one thing. See, this is the mass of the alpha particle, right? Now, what is the mass of the proton? Is 1.67 into 10 to the power minus 27 kgs. Just check what is the ratio of M alpha by MP. So 6.69 into 10 to the power minus 27 divided by 1.67 into 10 to the power minus 27. So it comes out to be roughly equal to 4. Therefore, the mass number for alpha particle is 4 times protons, that is hydrogen, right? So this is the thing which I want to cover, and this is the last question of today's class. So this question says that what is the charge to mass ratio of electron? Use that value to compute the angular frequency if the magnetic field is 0.004 Pascal. Okay, so the charge to mass ratio of electron, let us calculate. Charge to mass ratio of the electron, so it is QE by ME. We know that QE is 1.6 into 10 to the power minus 19 coulombs. ME is 9.11 into 10 to the power minus 31 kgs. So let us just write it properly. So how much it comes out? 1.6 divided by 9.11. So it comes out to be 0.1756, and 31 minus 19 is 12. So it comes out to be again 1.756 into 10 to the power 11. This is the charge to mass ratio coulomb per kg for the electrons. Now I have to calculate the angular frequency. So omega c again is QEB by ME. So QE by ME is already there. So just put this 1.756 into 10 to the power 11 times 0.004 Tesla. So just 1.756 into 0.004 if you do, so it comes out to be 7.024 into 10 to the power minus 3 into 10 to the power 11. So it comes out to be 7 into 10 to the power 8 radians per second. This is the answer of this question. So mostly we have seen the numericals which will be helpful in solving the assignments of week 11. Particularly the numericals are based on these cyclotron frequencies, this charge to mass ratio kind of thing, and radius of gyration based questions are there, kinetic energy based questions are there in the radius of gyration, how the formula has improved if we put the kinetic energy instead of velocity. So these 5 numericals will be extremely helpful for solving the assignments questions. And before that, what we have done, let us see. This is for the non-homogeneous fields. One of the important criteria which needs to be satisfied, that is the radius of gyration should be much less than L. What is this L? Is the scale of inhomogeneity. That is the length up to which the B is homogeneous. After that it is non-homogeneous. And drift of the guiding center expression is given here. Drift velocity is this. Omega c is qb by m. We have already seen. And in case of electric and magnetic field which are perpendicular, electric field and magnetic field are perpendicular, where E is in xz plane, B is in the z axis, we can see that the Vz is similar to that of the electric field in the z direction. It's quite similar to that. But the Vx Vy expression is kind of an oscillatory expression, except for this extra term which is there, Ex by B. Okay. And before that I have listed the formula for the cyclotron angular frequency, the frequency, time period and radius of gyration. And we have seen that for the ions the radius of gyration will be greater than that of the electrons because their mass is more. Okay. But most important thing is that the m by q ratio is what actually matters. Okay. And this guiding center is that imaginary point above means surrounding which the circulation takes place. So ultimately, in case of uniform and static magnetic field, you have this helical motion. In the z direction, it moves with a constant velocity, and Vx Vy performs a circular motion, which we have seen here. So it gives a helical path, and this is the radius of gyration. So radius of gyration is nothing but the radius of the circular motion. Okay, so this is what is there. And in the uniform electric field case, we can see that only in the z direction the motion exists, and in the other direction that is constant. Initially, whatever the velocity were there, it is the same, and in the z direction only, it is going linear with time. Energy is conserved in both the cases when we are taking separately, when taking the uniform and static magnetic field. Here also, when we are taking the uniform and static electric field, the energy is conserved, work done net is 0. So these two we have seen. Before that, when we will consider these particular cases like electric field and magnetic field and particle is going there, well, we can do it the particle description of plasma only when the concentration of the electrons or ions are very less in number. And before that we have solved all the assignment questions which are there. And so this is whatever I have for today. And yeah, so yes, these numericals are of course helpful, the last 5 numericals which are there, and some expressions which I have written, that is also quite helpful. So I am stopping here. Save it. Okay.